Okay, so linear algebra is a way of abstracting certain types of problems. And we're really going to first start out with systems of linear equations as the problem that we're going to solve. And the notation we're going to aim for is a matrix times a vector equals a vector. And we'll define these. But this is the first fundamental thing in linear algebra. And we're going to look at this equation where we have some matrix times a vector equals a vector. And so we'll develop what a matrix is, and we'll develop what a vector is, and then we'll have to talk about what solutions are. And then the second problem that linear algebra tries to address is a matrix times a scalar is equal to that same scalar times a vector. And these are called eigenvalues. And the solutions that come out of it will be eigenvectors. And that's kind of, this course is split between these two ideas. Now, these ideas are extremely generalized. So we're going to start with system of equations, but we'll see that more can be done with this than systems of equations. So the first thing we're going to do is we're going to define a system of equation. So from regular algebra, we have the ability to have two systems, two equations that are linked in variables. Whatever happens to x in one variable, one equation happens in the other. And so we want to think of what can happen for a solution. So let's look at this system visually. So the first equation, number 1, if I change that to a linear form, so it's going to have an intercept at 3, 3, and at 3/5. So let's see, that's about 3/5. And anything along this line, all right, we have a slope of -5, and we have x and y intercepts that define the second equation, or the first equation. The second equation transforms to y equals 2x plus 4. So it's going to have an intercept of 4 and a slope of 2, so 0, -2-ish. Anything along this line satisfies the second equation. What we end up with is a point of intersection. And that point of intersection is a solution to the system. We want to find some space or some place that solves the system of equations. Now, there are other types of solutions or other type of behaviors a system can have. And just graphically, we can have the system consists of lines that are parallel, so there's no overlapping or no solution to the system. The other thing we can have is the first equation in the system, and the second equation in the system are exactly the same line. And so we get, in this case, the set of all real numbers is the solution, because any value on the line will cover all real numbers. And so we actually have a set of, an ordered pair that is allowed to range across the equation that it reduces to. And this is our first look at these. So what we want to do is we want to get some notation so that we can generalize this idea of a system of equations and see what we can abstract out of it. So what we're going to do is we're going to say in the xy plane, any straight line has the form some coefficient times the x variable plus some other coefficient times the y variable that's equal to some constant. And so in this case, A1, A2, and B are real numbers. And both A1 and A2, we shouldn't say both. How do I want to phrase this? Not both A1 and A2 is 0. One of them can be 0, but both can't be. And so an equation in this form is a linear equation in x and y. But our algebras aren't limited to linear things, and we're not limited to the xy plane. We can have multivariables. We can talk about a three-dimensional space, a four-dimensional space. And so what we can do this for is we'll say a linear equation in its general form, not just in the xy plane, can be expressed as A1 x1 plus A2 x2. And so we're going to number our variables because we can have multiple variables. In fact, we can go all the way up to n variables equal to some constant. We can call the variables unknowns, and in this case, right, because we might be run out of alphabetical letters, so we want to be able to talk about any number of unknowns. So, for example, I can have a linear equation that looks like this. I can have a linear equation that looks like this. And I can have a linear equation that looks like this. Here we have two unknowns, three unknowns, and 4 unknowns. Now, what we'll note is that there are no products or roots or powers of the variables. So, I'll do this in red, not linear equations. Because of the square root in the y variable, this is not linear. Because of the multiplication of xy, this is not linear. And because this variable is going into the sine function, this is not linear. So these are examples of things that would not be linear equations. And what we want to do then is a solution of a linear equation is a sequence of numbers number 1, number 2, all the way up to number n, such that the equation is satisfied or still holds true when we substitute x1 equal to s1, x2 equal to s2, xn equal to sn. So one sequence is a singular solution, and the set of all solutions, so we can have multiple sequences that solve this, is called, the set of all solutions is called the solution set. So let's find a solution to a system, to a linear equation. Not a system yet, but just a linear equation. So 4x minus 2y equals 1. So to find a representation of the full set, what we can do is we can make x equal t. We're going to make it a parameter. And if we plug this in, then we can find y. So I'll do some rearranging. 4x minus 1 equals 2y. And so 4t minus 1 equals 2y. So y equals 2t minus 1/2. And so now we have a formula that, using an arbitrary number or a parameter, gives any specified values that we need. So we can see this is the set of t, comma, 2t minus 1/2, which would satisfy x1 and x2, or in this case x and y. So for example, if t was 3, then I would get 6 minus a half. So 6 minus a half is what, 11 halves? And that's one solution. But this set contains all possible solutions by using a parameter t that we can use to find it. Let's look at another example of a system, or not system, of a linear equation. So let me change colors here. So if I have x1 minus 4x2 plus 7x3 equals 5, then I'm going to want to assign some parameters. Now, since I have 3 variables here, I'm going to start at the back end, and I'm going to say x3 will be a parameter t, and x2 will be a parameter s. And if I do some rearranging here, x1 equals 4x2 minus 7x3 plus 5. And that means x1 is equal to 4s minus 7t plus 5. And now I have 3 numbers that are defined by 2 parameters, s and t. And one of the things we're noting here is the number of parameters seems to be related to the number of variables. And so this is what we mean by a linear equation and a solution to a linear equation, where we can write it in the most generalized form by using the parameters. And this generalization is going to help us abstract some things that are going to be common to linear equations. Next segment, we're going to look at how we can apply this to systems of linear equations.